In this discussion, we will talk about solving exponential equations. So first of all, let us define what an exponential equation means. So definition is, an exponential equation is one in which a variable occurs in the exponent. So let's talk about, at least give you two examples to illustrate what an exponential equation means. Let's say our first example is 2 to the power of x equals 8. Now if you notice, the exponent x shows up as an exponent. The variable x shows up as an exponent. Now if you look at the second example, similar thing happens. Now let's make it a little bit more complicated looking. 5 times 1.2 to the power 3x minus 2 plus 94 equals 100. Now once again, if you look at the exponent, it has a variable attached to it. Now let us look at a simple example with the perspective of solving it. So let me call that as example 1. So let's say we have 5 to the x power equals 5 to the third power. Since we have the same basis, we could set the exponents to be equal to each other. In other words, x could be 3. Now this kind of idea could be used as long as you have the same base and the base is positive. Now the property that we use here can be summarized as like this. If b to the power of x is same as b to the power of y, then those two exponents, x and y, must be equal to each other as long as b is a positive number and is not equal to 1. Now let's look at our second example. We have 3 to the x power equals 27. Now if you notice, 27 could be written as 3 to the third power. So we could write as 3 to the x equal 3 to the third, and we could still use the same property as we discussed, x supposed to be equal to 3. Now let's introduce another example with the exponent to be an expression. So let's say we have 5 to the power 2x plus 1 equals 25. Again, which could be written as 5 to the second power. If you make those two exponents to be equal to each other, we will have 2x plus 1 equals 2. Therefore 2x equals 1. So x becomes 1/2. Sometimes it is not so much the same exponents you will have. You may have to use some properties of exponents. So let's look at the fourth example, where you have 2 to the power 3x plus 2 equals 4 to the power 3. Now here, if you notice, we don't have the same base. Now, however, we do know we can write 4 as 2 to the power 2. Then, so it will look like 2 to the power 2 to the third. If you use one of the rules of exponent, you are allowed to multiply 2 times 3 and get 2 to the power 6th power. Now we could say, alright, 2 to the power 3x plus 2 equals 2 to the 6th. So what that means is, according to the property that we have been using, 3x plus 2 is supposed to be 6. So 3x is 4. So that will say x is 4/3. Now let's think about another example. Let me call that is example 5. So we have 4 times 2 to the power 8x plus 1 equals 8 to the power 3x. Now if you look at these bases, we have 4, 2, and 8. Now we can think about a common base. as you know, 4 could be written as 2 to the second power, and 8 could be written as 2 to the third power. So if we did make 2 as our common base, we will have 2 to the second power times 2 to the power 8x plus 1 equals 2 to the third to the power of 3x. Now, if you use the properties of exponents, when you multiply two exponents with the same base, we write the same base and add exponents. So if you add 8x plus 1 and 2, I get 8x plus 3. And as we did before, we could multiply the exponents and write 2 to the power 9x. So using the same property, we could say 8x plus 3 equals 9x. Now, of course, if you move this 8x to that side of the equal sign, x becomes 3. Unfortunately, not all the equations could be expressed with a common base. Like, for example, let me say this is example 6. Let's say I have to solve an equation 2 to the power x equals 7. Now, as we know, 7 cannot be expressed as a power of 2. So we need to think about some other ways to solve this type of equation. Of course, you can use calculators to solve equations. That's not the point of our discussion today. So we are looking for algebraic method to solve this type of equations. To solve this type of equation, we need to learn about logarithms. The idea of logarithms could be used to solve this type of equations. So let me write some brief ideas about logarithms. First of all, let's talk about the definition of logarithms. The definition of logarithm is if b to the power y equals x, then in fact is if and only if log base b of x equals y. This is the basic definition. In fact, this is a very important definition that one has to keep in mind all the time when you are dealing with logarithm. First, let's know how to read logarithm. So if somebody writes log base b of x, so we read this as log of x base b or log base b of x. Either one is acceptable way of calling it. I'm going to be using, this is supposed to be x, using log base b of x. That kind of terminology I'm going to be using throughout this discussion. First of all, we have to understand that b is the base and b have some restrictions. So first of all, b should be a number greater than 0, and not only that, b cannot be 1. Now, if you learn a little bit more about exponents and logarithms, you will know logarithms are not defined for negative numbers. So in other words, x cannot be a number here less than 0. Let me write an example. So we all know 2 to the power 4 is 16. Based on this definition that I have here, we could write this as log base 2 of 16 is 4. Now if you really look at this expression, the question that we ask is, what exponent of 2 is going to give you 16? The answer is 4. So logarithm basically is finding the exponent of the base so that you will get the domain. For example, if somebody asks you a question, log base 10 of 1000, the question is, what exponent of 10 will give you 1000? The answer is basically 3. In practice, we commonly use or generally use two types of bases. One of the bases, base 10. And we use this a lot. So this is called common log. Now, for example, our previous example, log base 10 of 1000 is a common log because it's base 10. Now, since we use them a lot, we don't even bother to write the 10. So if you see something without a base, that means it's base 10. Next base is base e. And this is generally used for mathematical purpose as well as scientific applications. So, for example, log base e of 10, if somebody says, simply we write ln of 10. So, if you see ln means log base e. Now, if you look at your calculator, you will have both logs, base 10 and log base e. By the way, log base e is called natural log. Basically, it is used in several natural science. For our purpose, we also need to know one of the property of log. There are several properties, but this property that I am writing is very much used in applications. So if you have log base b of x to the y power, it could be written as y times log base b of x. In other words, the exponent y can be brought forward. So this property is something that we normally use or very much used in application problems. To solve most of the exponential equations, we follow a three-step process. First of all, we isolate exponential expression, take log both sides, and solve for the variables. So, to illustrate that idea, let me look at the next example. Let me call that is example 7. Let's look at example 6. It says 2 to the power x is 7. Now, this already have a situation. We have isolated the exponential expression, which is 2 to the x. Now, according to the steps we have suggested, take log both sides. So if we take log both sides, we have a situation like log of 2 to the x equals log of 7. Now, as we said before, the exponent that can come up front. So in other words, we'll have x times log of 2 equals log of 7. So x must be equal to then log of 7 over log of 2. Now to find this answer, you could use your calculator. And I think it is something like 2.81. So what we are saying here is, if you raise 2 to the power 2.81, we will get 7 as our answer. Now let's look at another example. I call it example 7. 5 to the x equals 3125. Now if you like to solve this as we did before, we take log both sides. Log 5 to the x equals 3120, log of 3125. So as again, this x can be brought up here. So x times log 5 equals log of 3125. So x in fact equal log of 3125 over log of 5, which will work out to be 5. So what we are saying here is 5 to the 5th power in fact equals 3125. So let's look at another example. Again, one more or few more. Example 8. We have 3 to the power x plus 1 equals 4 to the power 2x minus 1. Now if you notice here, we have different bases. We have 3 as our base and we have 4 as our base. Now, however, we have isolated the exponential expressions. So if we take log both sides, we will have come to a situation log of 3 to the power x plus 1 equals log of 4 to the power 2x minus 1. As we said before, we could bring both these exponents up front. So we'll have x plus 1 times log of 3 equals 2x minus 1 times log of 4. So if we continue with our example from the last page, we came to x plus 1 times log of 3 equals 2x minus 1 times log of 4. Now at this point we could just use your calculator to find log of 3 and log of 4. I'm going to use two decimal numbers. Log of 3 will work out to be like 0.48 times x plus 1 equals 0.6 times, approximately 0.6 times 2x minus 1. Now if you notice, this is a linear equation and you could easily solve for x. So let me quickly solve this. 0.48x plus 0.48 equals 1.2x minus 0.6. So if I combine like terms and move x one side and the numbers other side, we'll come to a situation where we write 1.08 equals 0.72x. So x in fact is approximately equals 1.5. We can revisit one of those equations that we dealt with using the same base as previously we did. Let's look at this example. 3 to the power 2x plus 1 equals 81. Of course, we could do this problem using the same base idea, where 81 could be written as 3 to the 4th power, and you could make 2x plus 1 equals 4 and solve for x from here. Now, I wanted to use the idea of logarithms as we discussed here. So let's use log both sides. Log of 3 2x plus 1 equals log of 81. Now, as again, we could move this 2x minus 1 as a coefficient. So we have 2x plus 1 times log of 3 equals log of 81. Now, if you wanted to separate, we could divide both sides by log of 3, and you will have a situation like 2x plus 1 equals log of 81 over log of 3. Now, that will equal to 4. So we will come to the same equation as we had it before. So we will have 2x plus 1 equals 4. So 2x equals 3. So x becomes 3 over 2. So we could use this idea even for the previous problem. That's the point that I like to make here. Now, this procedure that we did, it's not necessarily that we ought to always use log both sides. We can use ln or any other base that you wish. But usually we use log both sides, or you can use ln both sides. For example, if you have e as the base, it is advantageous for you to use ln as the log. You can use ln both sides. Now let me illustrate this another example here. It's a little bit complicated than what we did previously. So let's look at this example. We have e to the 2x minus 5 e to the x plus 4 equals 0. Then we are trying to find x here. Now, first of all, we had to recognize e to the 2x is same as e to the x to the power 2. This is coming from the properties of exponents. So in other words, if I call e to the power x as some other variable, let's say t, then e to the power 2x could be called as t squared. If I did that transformation, I will have t squared for e to the 2x minus 5 e to the x is t plus 4 equals 0. Now, this is a quadratic equation. You can easily factor out like t minus 4 times t minus 1 equals 0. So either t minus 4 is 0 or t minus 1 is 0. So this will lead us to write t equals either 4 or t equals 1. Now, once you have done this, we recognize e to the x is t. So we have a situation like e to the x equals 4 or e to the x equals 1. Now since we have the base as e, so it is advantageous for us to use ln both sides rather than using log. So if I use ln both sides, ln is another log with base e, so we will have a situation like this, or ln of e to the x equals ln of 1. Now, as we said before, we can always bring these exponents as coefficients, so we will have x times ln of e equals ln of 4, or x times ln of e equals ln of 1. Now, ln of e is equals to 1, and ln of 1 equals 0. If you use those properties, I will have x equals either ln of 4 or x equals 0. Now let's look at another example. I'm calling that is example 11. This is a little bit of real world application. So let's say Alex invested $5,000 at an annual interest rate of 3% compounded monthly. How long it would take this investment to reach at $7,000? So we are looking for the time. However, to do this, we need the formula to calculate compound interest. I'm not going to go into the detail of getting this formula and things like that. However, the formula that we are going to use is A equals P times 1 plus R over N times T, where A is the amount, P is the principal or the initial investment, R is the rate, and N is the number of compounding per year, T is the time. So if you plug in numbers from this expression, I will have A equals the amount which is supposed to reach at $7,000, and the P equals 5,000, that is the initial investment, and the R, which is 3% or 0.03, and the N is 12 because it is monthly compounding. So if you look at this formula here, we know everything except the T. So let's plug in those numbers and see what happens. So if you plug in A as 7,000 equals 5,000 times 1 plus 0.03 divided by 12 to the power 12t. Now, only unknown or the things that we like to solve is this t. Now, first task is to isolate the exponential expression. Remember, this is our base and this is our exponent. So we have to take this 5,000 out of the way. So what we do is we divide both sides by 5,000. So we will have a situation like 7,000 divided by 5,000 equals 1 plus 0.03 over 12 to the power 12t. I'm not going to really calculate this number. Rather, I will use calculator directly. Now, 7,000 over 5,000 is 1.4. Now, if I take logarithms both sides, I will have log of 1.4 equals log of 1 plus 0.03 over 12t. As we did before, we could bring this 12t as the coefficient using the property of logarithms. So we'll have 12t times log of 1 plus 0.03 over 12. Now, if you divide both sides by log base 1 plus 0.03 over 12, so we'll have 12t equals log of 1.4 divided by log of 1 plus 0.03 over 12. Now, if you use your calculator and calculate this quantity here, it will be equal to somewhere close to 134, if my calculation is correct, 0.757, I think, equals 12t. Now, if you need 12, you have to divide both sides by 12. So t will be approximately equal to something like 11.2 years. So this example clearly indicate how to use or how to solve exponential equation in a real world situation and find answers.